On to question 3. So carburization is a critical materials process. So one critical process when you're working with steel is carburization. So it's when you treat a material, presence of carbon monoxide, or charcoal. It absorbs and diffuses the surface of the material, makes the surface much harder. There are a couple ways you can do it, and you can model in this problem. So assuming the source of carbon is continuous supplied, concentration of carbon is equal to 0.3 mole fraction at the surface. So I'm going to say this is surface, steel is in black, carbon is in red. So at x equals 0, we have this constant source. So hopefully this is a very similar problem. Write down the boundary conditions of the PDE that you would solve to show how the concentration of carbon evolves as a function of time. So my PDE is dc dt is equal to dc, basically d squared c dx squared. So this is our partial differential equation, and we want to use our other expression, which is actually c squared d eta squared plus 2 eta dc. The eta is equal to 0. So where eta is equal to x over square root 4 dt. So this is our PDE that we want to solve for. This is our ODE that we want to solve for. So that's kind of the critical kind of idea that we're going to be working with here. So we want to state basically our boundary conditions as a function of our ODE. So I'm going to assume that steel is going to be relatively large. So I'm going to assume this is infinite. So x here is equal to infinity. Now, I can only invoke this assumption if my length of this distance here, if this length, L, is greater than 10 square root dt. So these are the times, assuming a diffusivity of carbon, these are the times where I'm going to be essentially, when my length is greater than 10 dt, this is when this solution is going to be valid. So what are my boundary conditions here? Again, I'm trying to plot, what I want to plot is the concentration of carbon as a function of, time, or actually, excuse me, distance x, and also as a function of time. So I know that initially, right at, let me erase that here. So right here at x, my concentration of carbon is 0.3. So this would be like at time, I'm going to draw this, my blue is at time t equals 0. So I just have my carbon here and then nothing, right? Because I've just started to kind of apply it to the source. At some time t equals, let's say 1,000 seconds, it's just start to kind of diffuse into your material looking like this. So this is, t greater than blue, and then my green would be t greater than, my yellow or whatever, orange, it would be even further. So here, my time is increasing because my material is diffusing it. So that's how the concentration profile should look like. But our boundary conditions are going to be the concentration of carbon at an eta equal to 0 should be equal to 0.3. And what's our concentration at infinity? So concentration of carbon where eta is equal to infinity, well, that should be equal to 0. So those are our boundary conditions. We could plug those in. You could use Mathematica and we could kind of solve that. But again, those are kind of the assumptions when our solution is valid, and we could see the schematic in kind of below. So we've written the boundary conditions, the PDE we need to solve, and how the concentration is a function of distance and time. So that's how you would draw out this problem. So again, we've only done a couple problems in class, so maybe a diffusion couple. Maybe you want to kind of study that one. So anyways, now, I love this next problem. Turns out from my application, I actually only need 0.1 mole fraction to carburize my steel. So I need 3, basically mole fraction of carbon. So 1 mole fraction of carbon. So I measure the concentration of carbon versus depth below, and in this next plot, we're going to see the implantation depth is the initial amount of carbon implanted in my material, and then I anneal to diffuse carbon further in my material. And I'm asked to estimate the activation energy of carbon. So we know that, let's go down to our graph here. We have this graph of mole fraction. We know that we're focusing on this here, and we have this square as implanted. So we can see that we initially implant, let's say this is an order of magnitude. Let's just say that this distance is like 200 nanometers. So that's our distance, our x. So whenever we hear implant, we should remember engineering approximation, 2 square root dt. So we want to kind of remember that expression. Again, that was back in lecture 4. Our engineering approximation, if we're trying to implant, diffuse, physically dope to kind of some constant, value, we're going to use back to our engineering approximation here. our engineering approximation over here, x equals 2 square root dt. So let's go back to our exam practice. So we're going to use this expression because we have this implantation depth, and then we anneal it at different times, different temperatures. So when we go from here to here, so implanting from here to here, we travel, let's say this is an additional distance. Let's say it's like, this looks pretty much like, let's say 150 nanometers. So we travel a distance x, or an additional implantation depth, 150 nanometers for a time equal to 65 hours, and then at a temperature of 780 degrees C. So we know that D is equal to D naught times exponential minus QA over KT. So we're going to need to use this expression, and we're going to need to figure out the diffusivities at a couple different temperatures, and then figure out how we can calculate the activation energy and solve for the problem. So let's go ahead and do that. So we know this first kind of expression here at a distance, as a function of time. Let's kind of draw the straight line to see where we this is kind of a nice distance. This distance travel is probably about, say our x here is pretty close to 400 nanometers. So the additional implantation depth. So now, what is our time here for this kind of circle? So this is a temperature equal to 1000 degrees C and a time equal to 0.5 hours. So let's go ahead and kind of plug in this information, Mathematica, and then let's kind of calculate it. So I'm going to go over here. So I have this expression. I'm going to actually close it a little bit more. So I have an expression now where I'm going to use, so let's go ahead and calculate this first one. So solve for when, so we need to have x, which is, let's go to our engineering approximation. So our x, which was equal to 150 nanometers, so times 10 to the minus 9, set it equal to 2 times square root of d1 times t, and our time here is going to be 65 hours. So that's quite a while. So 65 hours times how many? Let's do this. So we want, again, everything in meters and seconds, and so I want to do 65 hours. So 60 minutes an hour, and then 60 minutes an hour, 60 seconds per minute. So I believe, hopefully that's right. We could Google and make sure that that's the case. So let's just do 65 hours to seconds. So let's just make sure, pull this out. Again, this will be our value. We could just double check this. There we go. We could just feel good about our math. So anyways, let's go back to here. So I've got my value, and then that's our time. So let's go ahead and solve for D1. So our D1 is equal to, let's just do this numerically solve, make it perhaps a little bit easier. So that's our D1. We could do a very similar thing for our D2. The only thing we changed is 400 nanometers. And then now we have the number of hours changes to 0.5. And then our temperature is going to be different as well. So let's call this D2. So I'm going to call and define some variables. Oops, just define this here. So my D1 is equal to this. D1 is this. My D2 is going to be this. So let's go ahead and plug that in here. My D2 is equal to here. So now I can now solve for, so I need to solve simultaneously that basically D1 is equal to D naught. D1 is equal to D naught times exponential K. I'm going to put in K is our Boltzmann's constant, 1.38 times 10 to the minus 23. So equals minus QA divided by K times, what's our temperature here? In the first problem, 780. So let's go ahead and look at that. So 780 plus 273. And then now we can solve for D2. Set it equal to right here. And we could set this equal to our temperature is 1000. So let's go ahead and put a little parentheses around that just to make this nice and safe. Right here. And then we can solve this here. And then let's solve it for, we can solve for D naught and QA at the same time. Oops. Let's go ahead and let's gonna solve for these different variables here. So let's solve for QA, excuse me here. Ooh, actually, let me do D naught. Let's do numerically solve. I think we're going to need actually reals. There we go. So we've got our values. So D naught, QA, there we go. This is our activation energy. So you can solve problems like this, and I love this problem. Very, very difficult one. Again, there are going to be some problems in the exam you may not be able to do, but again, try to relate and relate and see if you can kind of develop a relationship or derive a relationship to kind of calculate those values. So last one, draw the relative. Of course, I didn't forget about Kirkendall. So I have a diffusion couple. So I have right over here, I have carbon on the right. I have steel on the left. So steel is Fe and iron, but you could kind of just generalize it as Fe. So I need to actually, let's go ahead and I'm going to erase a little bit here and give me some room. This is the beauty, or actually not the beauty. On the board, it's a little bit nicer in person. I get to move around and erase, but now I'm just using my little pen. But I do like to kind of record these videos from home. That's nice. Anyways, so I've got diffusion couple. I have got carbon on the right. I've got steel on the left. And now I'm going to draw essentially, or figure out kind of these fluxes. So what do I know about the diffusivities of carbon and steel? Carbon smaller than Fe, so diffusivity of carbon is greater than diffusivity of iron. So if I know that, I know my fixed first law. Again, this is why it's useful to kind of draw out and include these relationships. C dx. So I know that this is going to have a very, very large flux. So the flux of carbon in the C frame is going to be in this direction. So I'm going to go from left to right. The flux of iron is going to be a little bit less. So flux of Fe, excuse me. Let's keep our notation correct. So flux in the C frame of iron is going to be here. And what is our condition for in the C frame? Vacancies have to move in this direction. So flux, vacancies, C frame. So I need this flux, and this flux to sum to equal to 0. So those are my relative fluxes. I'm using the C frame. What direction and what's going to kind of happen here? So let's finish up the question. What direction will the interface move? Well, I know that if I have lots of atoms moving here, I'm going to be basically filling up. So I'm going to be my atoms, if I have these extra, again, let's draw our extra half planes. So if I have these extra half planes, so if I've got lots of atoms moving over this side, I'm filling up these extra half planes here. The atoms are leaving and vacancies are moving to this side, so I'm destroying planes here. So that means what? So this side, I am filling, and then I'm expanding. This side, I am destroying and shrinking, basically shrinking. So what's going to happen? All the atoms move around on this side, more vacancies kill up these atoms over here. We're expanding on this side, so we're going to move, the interface is going to move to the right. So let's see if we could kind of answer the rest of our questions. Describe what occurs in the drawings and what is happening, using drawings of what is happening at the atomistic level. Where will Kirkendall pores form and where? So if I have a lot of these, create or destruction of half planes, if I have a long enough time and my temperature is high enough, so I have long time, high temperatures, I can form Kirkendall pores and they will form on this side. So the pores will form on the C side. That's it. So again, hopefully this was helpful. And now we're going to get into our last problem, which is phase diagrams. So remember, Kirkendall is definitely going to show up. You're going to have one of these problems that's probably going to be an ODE problem, basically defining essentially concentrations or setting up boundary conditions, and then maybe an activation energy problem. I can't help myself. I love Arrhenius relationships. So next time, phase diagrams, and then that'll be it for your exam one. You'll do great. Thanks. I'll see you in the next video.